here's the rule. So Lobitel's rule just says, if the limit as x approaches a of f of x over g of x is either 0 over 0 or infinity over infinity, it can actually be positive or negative infinity on the top or the bottom. Doesn't matter if it's positive on the top, negative on the bottom, or vice versa, right? They can both be positive, both be negative, or one of each. If your limit is a 0 over 0 indeterminate form, or an infinity over infinity indeterminate form, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, provided this limit exists. So that's the whole thing. If you have a limit that's a 0 over 0 or infinity over infinity, you can take the derivative of the top, the derivative of the bottom, take the limit of that, and the answer is the same. We're not going to prove it because the proof is rather complicated and tedious, but we're going to at least think about why it might be true. So we can explain this infinity over infinity case by the following thought experiment or just idea. Imagine there are two cars, A and B, traveling for an infinite amount of time. Okay. And A of t is going to be the distance that car A travels. A prime of t is the velocity of car A. And B of t is car B's distance traveled. And B prime of t is car B's velocity. Suppose that car A travels twice as far as car B. So right, they're going and going and going. Car B goes infinity miles and car B goes twice, right? I mean, it's gone twice as far, even though they've both gone an infinite distance. So the ratio of their distances to each other should be 2, right? If you look at how far A went and how far B went, their quotient, if you take the limit of it, right, A's gone twice as far, so that fraction should be 2. Now here's where we're actually going to do some thinking. If A's gone twice as far as B over an infinite amount of time, that means that A had to be going twice as fast as B. If they're traveling forever and ever and ever, and car A has gone twice as far as car B, its speed had to have been twice as fast essentially the whole time to have gone twice as far. And that's the whole idea, is that this limit of the distance over the distance being 2 means that the limit as t goes to infinity of the velocity over the velocity also has to be 2, because A's velocity has to be twice as fast as car B. So that's a very, very broad strokes kind of, here's why how you can kind of understand Lobitel's rule actually working. You don't need to actually know this to use Lobitel's rule, but it's kind of nice to be like, okay, that seems at least like it kind of makes some amount of sense. The important thing to remember about Lobitel's rule really is that you can only ever use Lobitel's rule when you have a limit, right? It has to only for limits. Limits and Lobitel both start with L. It's a good thing to remember, right? So you can only use Lobitel for a limit, and it has to be a fraction that is either 0 over 0 or infinity over infinity. Cannot be anything else. There are other expressions that we can manipulate so that we can then use Lobitel's rule. But if it doesn't look like one of these two things, Lobitel's rule is not on the table. Okay. Yeah.
So, like 0 over infinity or
Those are not indeterminate forms. So if you had so in fact, let's actually do a couple. So if I had, let's do this. So if I had the limit of, say, limit is x goes to, for a second, let's do that. Limit is x goes to infinity of, now I'm like, what am I going to do? I had an idea and now I've lost it. Let's say 0. Sorry, I'm trying to think of one. I mean, it's kind of silly, but okay. 1 over x squared. Welcome. That's a 0 over infinity, right? The numerator is going to 0. The denominator is going to infinity. What's 0 divided by 5? What's 0 divided by 7? What's 0 divided by any non-zero number? 0, right? Because when you have 0 divided by not 0, you're saying, how many times does this not 0 number go into 0? And the answer is 0 times. So if your denominator is really, really large, it's going to go into 0 0 times. The other way to think about this, though, is that if you have a very, very small number divided by a very, very large number, the result should be very small. In a similar way, I could ask, what's the limit as x approaches 0 from the right of the natural log of x divided by x? Why 0 from the right? Because the natural log is only defined when x is larger than 0. Now, this might look like a L'Hopital's rule kind of question. It's not. This isn't a 0 over 0 form. If you think about the natural log function, that's what natural log of x looks like. So as x goes to 0 from the right-hand side, what's the natural log function doing? Going to negative infinity. So we're going to get a negative infinity divided by 0, a slightly positive 0, if you will. So when you have a really small number divided by a really big number, the answer is very, very small. When you have a really big number divided by a very, very small number, the answer blows up. In fact, you don't even really need the big number part here. If you have just a regular number divided by a very small number, the answer blows up. So is my overall result here very, very large or very, very negatively large? Well, I guess is it positive or negative? It's negative, right? Because it's negative on top and it's definitely positive on the bottom. The negative divided by positive is negative. That's going to be a negative infinity. So when we have these types that are not L'Hopital's rule types, they're not indeterminate forms, you just kind of have to talk it out. If you say, oh, I've got small over big, it's small. If I've got big over small, it's big. Just to point out, if you mistakenly use L'Hopital's rule here, so if I said this was equal to, and so when I use L'Hopital's rule, I write an L apostrophe H above the equal sign to show that I'm using L'Hopital's rule. If I did that, I would get the limit as x goes to 0 from the right. The derivative of the natural log of x is 1 over x. The derivative of x is 1. And as x goes to 0 from the right, 1 over x goes to positive infinity. So this limit would be positive infinity, which is not the correct answer. So we can't use L'Hopital's rule in the situation where we can't use L'Hopital's rule, right, where you don't have 0 over 0 or infinity over infinity to begin with. Yeah.
If we're looking at zeros from the right, why are we looking at the? I don't know if I'm thinking about this right, like the bottom part and the top part.
Well, because x approaches 0. So we're coming at 0 this way. We're saying, oh, what's the function doing? What's the y value doing? Oh, it's doing that. That makes sense? Okay. Oh, this pen looks a little leaky here. It's no good. All right. Well, let's actually use some examples where we can use L'Hopital's rule. So let's say we want to find the limit as x goes to infinity of 6x squared plus 5 over 2x squared plus 1. Now, this is an example that you probably already know the answer to. Can you guys show me on your fingers what you think the answer might be? Yeah, it's good to guess. Guesses are good. You guys can show right in the chat too. Do you guys have guesses what this is? Anybody in the chat? You guys are like, no, I'm just here to watch the class. Okay, fine. The answer is 3. And this is one of those limits where if x is going to infinity and the degree on top and the degree on the bottom is the same, the limit is the quotient of the leading coefficient, which is 6 over 2, which is 3. But you could also use L'Hopital's rule. Do you have to use L'Hopital's rule? Not really, but it's nice to see that it works for things where it should work. I guess I should really point out, first of all, can I use L'Hopital's rule? Yes, I can, because the top is going to infinity and the bottom is going to infinity. So this is an infinity over infinity form. And then I'm going to take the derivative of the top and get 12x. The derivative of the bottom get 4x. I'm going to cancel the x's because why not? And that's the limit as x goes to infinity of 3. The limit of a constant is just the constant. So we get 3, just like we already knew the answer was. What about the limit as x goes to infinity? I'm actually going to write this one in a slightly misleading way of x squared times e to the negative x. At first glance, we can't use L'Hopital's rule. We don't even have a fraction. But I should ask myself, well, what kind of form do I have? So what's happening with x squared? Is it getting really large or really small or really negatively large? Those are kind of the things. So when we're doing L'Hopital's rule, typically you're looking for infinity over infinity or 0 over 0. Either things are going to infinity or to negative infinity or to 0. Which of those three things is x squared doing? Right. Which of those three things is e to the negative x doing? Think about the graph of e to the negative x, which looks like e to the x but flipped. So as x goes to infinity, what's happening with e to the negative x? It's going to 0. So this is an example of what's called an infinity times 0 form. What's infinity times 0? So what I want to point out is it's not really infinity times 0. Because we're not really multiplying by 0. We're saying it's a very large number times a very small, but still not 0 number. And a very large number times a very small number, anything could happen. It could be very large. It could be very small. It could be somewhere in between. So what we need to do is rewrite this in a way so that we can use L'Hopital's rule. And it's pretty straightforward here. It's going to be the limit as x goes to infinity of x squared divided by e to the positive x. Because now it's an infinity over infinity form, which is totally something we can use L'Hopital's rule on. So if I use L'Hopital's rule, my L apostrophe H there, I will, minor thing, not important at all, but I would encourage you all to say L'Hopital, not Le Hospital, as some people like to say. It is a French name. It is pronounced L'Hopital. So L'Hopital's rule says we're going to do the limit. There's always a limit, right? If you're using L'Hopital's rule, you should be writing a limit, and then whatever you've got. The derivative of x squared is 2x. The derivative of e to the x is e to the x. And it's still an infinity over infinity form. So we do it again. So typically, after you've used L'Hopital's rule, the first thing you should do is try to then evaluate the limit. Can you let x be infinity and get an answer? The answer here is no. If x is infinity, I get infinity over infinity. This is still infinity over infinity. So I use L'Hopital's rule again. And we have the limit as x goes to infinity of 2 over e to the x. And now if I let x go to infinity, what do I get? 2 over infinity, which is going to go to 0. I don't really like to write 2 over infinity. I would just say it's equal to 0. And we're done. That's our answer. As x goes to infinity, x squared over e to the x goes to 0. What's kind of interesting about this is that that fact is actually true for any power of x over e to the x. If you were to do the limit as x goes to infinity of, say, x to the 100th power over e to the x, well, every time you use L'Hopital's rule, or I should say, we can use L'Hopital's rule because it's infinity over infinity. And every time we use L'Hopital's rule, the bottom isn't going to change. The derivative of e to the x is e to the x. But the numerator, the power of x is going to be 1 less every time we use L'Hopital's rule. So that's going to be 100 times x to the 99th power. And then in the next step, I'm going to get the limit as x goes to infinity of 100 times 99 times x to the 98th over e to the x. And I think you can see where this is going. I'm going to do this probably like 98 more times. Not really. But after 98 more steps, right, we're going to get to the point where we have, okay, 100 times 99 times 98, all the way down to like 2 times x to the first over e to the x. Oh, sorry, I forgot the limit. And then finally, the last step is going to be, I'm going to have the limit as x goes to infinity of 100 times 99 times 98 times all the way down to 3 times 2 times 1 times x to the 0. I'm not going to make x to the 0 over e to the x. Okay. Where's the bottom going to? Well, just like it has in every step, the bottom is going to. And what's the top? I mean, it's not a small number if it's a constant, right? It is definitely a constant. And a constant over infinity, the constant always loses. So that's going to go to 0. Even if it's a really big constant. I should point out, because this will come up later, this number here specifically, 100 times 99 times 98 times 3 times 2 times all the way to 1. There's a name for that. It's 100 factorial. So when you have a number with an exclamation point after it, we read that as that number factorial. And it literally just means that number times the next smallest number times the next smallest number all the way down to 1. That's a little off kilter here. There we go. That will come back in 17C, in like the last 3 weeks of 17C, when you start talking about counting things and probability and combinations. It's not a huge deal, but it will come back around. So what this actually kind of says to us is that, x to any power is always overcome by an exponential function, right? No matter what, x to the 100th, x to the billionth power. If you graphed it, it would be ridiculous. If you graph it, like if you zoom out, like x to a large power, it looks like it's way bigger than e to the x for quite a while. But if you zoom out far enough, eventually e to the x overtakes x to a really large power. Always true. And we can know that's true because of what we did here, right? This limit being 0 shows me that the thing on top is eventually going to be way smaller than the thing on the bottom. So this tells me, oh, the top is way less than the bottom. And that's often the piece of information you take from these limits, is that when you take a limit like this and you get 0 eventually, it means the numerator thing is way smaller than the denominator thing. Or if you get a limit that ends up being infinity, it means that the numerator thing is way bigger than the denominator thing. Like this example. The limit as x goes to infinity of x squared over the natural log of x. Now, this one shouldn't be a surprise. If you think about the graphs, well, I know we haven't done it yet, but before we do it, I'm going to tell you the answer isn't going to be very surprising. Here's what x squared looks like. And here's what the natural log of x looks like. If you do these values divided by those values, it's going to be really big, right? These values are much, much, much like, right? If you plug in, let's say we plugged in e just for fun. We plug in e, the y value there is 1. The y value there is e squared, which is close to 8. And e squared divided by 1 is e squared, which is close to 8. So even just not even that big, right? This limit is already having largish values. Definitely infinity over infinity type, because even though it doesn't look like it, the natural log of x does get infinitely large as x goes out to infinity. It just takes forever, literally, right? But if we use Lobitel's rule here, the derivative of x squared is 2x. The derivative of the natural log of x is 1 over x. Can I use Lobitel's rule here? See, where's the top going to? How about the bottom? So I can't use Lobitel's rule. What I typically should do, so if I can't use, or I should, what I really should have done is if I plugged in infinity, which you just said, infinity over 0. What I really should do in this case, even though you could say infinity over 0 goes to infinity, it's better if we simplify this. I'm going to rewrite this as the limit as x goes to infinity of 2x times x, which is the limit as x goes to infinity of 2x squared, which then is more obviously, oh, that's infinity. Questions so far, either from you all or from the people on Zoom? So I will kind of preface this next part with, most of the L'Hopital's rule limits you probably encounter in this particular class are when you're having a limit as x goes to infinity. Because most of the time in this particular class, we're interested in what's the long-term behavior of some population versus some other population growth-wise. So that's often why you're taking limits to infinity. Again, especially in 17C, we start talking about like if you have like a predator-prey situation and you're asking what's like the long-term stability of the predator and prey population, you're going to be taking the limit as time goes to infinity and seeing kind of what your result is. That said, you don't have to have a limit to infinity to still be able to use L'Hopital's rule. So let's look at some other examples that don't have x going to infinity, like the following. Well, here's one that should look vaguely familiar. The limit as x goes to 0 of sine x over x. I think we talked about this one a while ago. This is a limit you're probably expected to know. Can anyone tell me what it is? It's definitely 1. We know it's 1. We might have shown it was 1, but now we can use the L'Hopital rule and say, okay, well, I should point out, we can use L'Hopital's rule because it's a 0 over 0 type of limit. Sine of 0 is 0, and x being 0 is definitely 0. We have 0 over 0. If we use L'Hopital's rule, we get the limit as x goes to 0 of the derivative of sine of x is cosine of x. The derivative of x is 1. And then plugging in 0, right? Because I can't use L'Hopital's rule again. It's definitely not a 0 over 0 or infinity over infinity. Plugging in 0, I get cosine of 0, which is equal to 1. So it's good to see that L'Hopital's rule still gives us the same results for limits we already knew. Let's look at another example. The limit as x goes to 2 of x squared plus 3x minus 10 over x squared minus 4. And I'm going to point out, you could also do this one without using L'Hopital's rule. Here, if you plug in 2, you do get 0 over 0. Right? 4 plus 6 minus 10 is 0. 4 minus 4 is 0. How could I do this without using L'Hopital's rule? What could I do to the polynomials in the numerator and the denominator? Not quite. So oh, that's actually an excellent point. So a lot of times people mistakenly say that this limit is equal to 1. Because they're like, oh yeah, the limit of the thing of polynomial is the quotient of leading coefficients. That's only true if it's the limit as x goes to what? Not 0, infinity. Right? So if x is going to infinity, in fact, I want to make this really clear because I've seen way too many students make this mistake in the past. So limit as x goes to infinity of x squared plus 3x minus 10 over x squared minus 4 is equal to 1. And either you could use L'Hopital's rule there, right? You could say limit as x goes to infinity of 2x plus 3 over 2x, and that's the limit as x goes to infinity of 2 over 2, and then that's just 1. Or you could do it the old school way and divide everything by the biggest power of x and get x squared over x squared plus 3x over x squared minus 10 over x squared all over x squared over x squared minus 4 over x squared. And if we simplify that, you get 1 plus 3 over x minus 10 over x squared over 1 minus 4. That's a lot of work, right? But we get the result that all these things, since x is going to infinity, all these things are going to be very small. So we're left with 1 over 1. On the other side of things, that's not going to happen here. So here you could either do this. Well, in fact, let's just use L'Hopital's rule first and see what happens. Using L'Hopital's rule, we're going to get the derivative of the top is 2x plus 3. Derivative of the bottom is 2x. Can I use L'Hopital's rule again? I mean, I did over here. Can I over here? I can't. Because here I use it again because I still have infinity over infinity. But here, if I plug in what x is approaching, what do I get? 7 over 4, which is certainly not 0 over 0 or infinity over infinity. That's it, we're done, that's our answer. Now, you could have also done this one by factoring and canceling. You could have said if the limit as x approaches 2 of the denominator factors is x minus 2 times x plus 2, the numerator factors as x minus 2 times x plus 5. And the x minus 2's cancel, and you plug in 2 for the remaining x's, you get 7 over 4. But yeah, I want to stress again, right, you can only use that trick about it being the quotient of the leading coefficients if the limit as x goes to infinity or negative infinity, but not to anything else. And specifically, it's because of this step right here, right? All the stuff at the end cancels out because x is going to infinity. All right. Some more examples. And then, oh yeah, okay. Let's look at this one. Limit as x goes to 0 of x minus tangent of x over x minus sine of x. Good times. So for some of these, it is going to be important to at least remember what sine and cosine and tangent of 0 are. So just a reminder, sine of 0 is 0, cosine of 0 is 1, tangent of 0 is 0 over 1, which is 0. And it's also good to know that cosecant of 0 is undefined, secant of 0 is 1, cotangent of 0 is undefined. It might come up. Definitely these will come up, maybe these will come up. So if I plug in 0, I get 0 minus 0 over 0 minus 0, which is 0 over 0. So we obviously need to use Lobitel. But I know I said this probably like 5 times already. I cannot stress enough. It's really important that you at least mentally ask yourself, can I actually use L'Hopital's rule before I go ahead and use it? Yeah.
So the reason that we don't say 0 over 0 or infinity over infinity is 1 is because it's not exactly the same thing. Right?
Well, because it's not 1. So what's 0 divided by 0? It could be 1, but it could be 7. Right? That works. 7 times 0 is 0. 0 minus 0 is 0. Check. Or my remainder is 0. That's accurate division. I mean, it's terrible, but like, right. So the whole thing is, what we're really saying with this is it literally is called an indeterminate form because the value is not determined, right? If you have a 0 over 0 type, the answer can literally be anything. Like in this previous example, this 0 over 0 ended up being equal to 7/4. But I could make up, like, you could pick a number, 9, and I could make up a fraction or a limit, a 0 over 0 limit where the answer was 9. For example, it's going to be kind of lame, but I could do the limit as x approaches. I'm just going to do it this way. So I want my answer to be 9. So I'm going to make sure there's, okay, fine. This is going to be kind of lame, but here's an answer where it's definitely 0 over 0 type, right? I can even multiply it out if you want. Right, that is an indeterminate form, but the limit is definitely 9, because if I factor out an x, I can then cancel these x's and plug in 0 and get 9. Or I could use L'Hopital's rule. Limit as x goes to 0, L'Hopital's rule drew the top is 2x plus 9 over 1. X goes to 0. Oh, I get 9 over 1. But again, the point is that when it's 0 over 0, the answer can be anything. Same is true for infinity over infinity, because sometimes one infinity is much larger than the other infinity. Like, I don't think I have an example of it actually. Like that first, there was a first example we did, like the limit as x goes to infinity of 2x squared plus 6 over x squared plus 1 or something like that. Right, this is definitely an infinity over infinity type, but that top is twice as large as the bottom, essentially. One way you could look at this part if you really wanted to is you could do some polynomial division. I know it's not super necessary, but I just want to show you guys real quick. If I do the polynomial division here, you can probably actually get it without doing the polynomial division. I'm gonna do it anyway. X squared goes into 2x squared 2 times. 2 times x squared plus 1 is 2x squared plus 2. Subtract, and you get a remainder of 4. So I could rewrite this limit as the limit as x goes to infinity of the quotient plus the remainder divided by the divisor. So the idea here is that 2x squared plus 6 over x squared plus 1 is 2 plus a little bit. And as x gets larger and larger and larger, that little bit gets smaller and smaller and smaller. So this ends up being 2 plus 0, which is 2. So this top part is literally, right, they're both getting infinitely large, but the top part's twice as large as the bottom part. I'm thinking about plugging in 1,000. You're plugging in 1,000, the 1,000 squared is 1,000,000. The top is 2,000,006. The bottom's 1,000,001. Oh yeah, they're both large numbers, but the top is clearly about twice as large as the bottom. So yeah, we can't say that 0 over 0 is 1 because it's not necessarily. It can be sometimes. Sometimes it's definitely 1, like sine x over x. But other times it's not, like if it was sine of 2x over x. That would be a different value. That limit would be 2. All right, so looking at this one, I'm going to use Lobitel's rule. I don't have any other good ideas. The derivative of the top is going to be 1 minus the derivative tangent secant squared. Ooh. And the bottom is 1 minus cosine of x. And that's still a 0 over 0 type. Because secant of 0 is 1 and cosine of 0 is 1. So we're going to do L'Hopital's rule again. And it's going to get a little bit messy. Could do that. No, that's lame. Don't do that. I was trying to use a trig identity there, but it's not really necessary. So the derivative of 1 is 0. Derivative of negative secant squared. So remember, we have some stuff squared. The derivative is going to be 2 times our stuff times the derivative of our stuff. So the derivative of secant squared is 2 times secant to the first times the derivative of secant, which is secant of x times tangent of x. And then the derivative of 1 minus cosine is much nicer. It's just going to be positive sine of x. Yeah, that's what I would do too. So here, this expression we couldn't really simplify, right? There's not really anything good to do here. You might be able to like multiply 1 plus cosine or something. I don't know. Here, on the other hand, if you start plugging in 0 again, right? Because I should definitely check, can I plug in 0 and get an answer? I don't. Secant of 0 is 1, secant of 0 is 1, tangent of 0 is 0, and sine of 0 is 0. So I still have a 0 over 0 form. But I really, really, really don't want to use L'Hopital's rule again, because taking the derivative of the top is going to get ugly. So what I'm going to do instead is I'm going to try and see if maybe I can simplify this a bit first. So what I really have here is the limit as x goes to 0. I'm going to rewrite this as negative 2 times secant is 1 over cosine. Secant is 1 over cosine. Tangent is sine over cosine. And dividing by sine is like multiplying by what? One over sine. Right? Dividing by something is like multiplying by its reciprocal. That seem okay? All right, well then look, I can cancel a sine. And then everything else left is cosine, and cosine of 0 is 1. So that's going to be negative 2 times 1 times 1 times 1, which is negative 2. Sometimes it really pays to simplify things, because definitely taking the, so we could have used L'Hopital's rule again, and it would have worked. Or you can totally take the derivative of the bottom and get cosine, and take the derivative of the top and get something terrible. And when you plug in 0 for x, you will get negative 2 over 1. But I don't want you to do all that work if you don't have to do all that work. So definitely sometimes it makes sense to simplify a thing before you keep going. Okay. So 0 over 0, infinity over infinity types, those usually aren't too terrible to deal with. No, not right. That's all right. But those aren't the only types of limits that sometimes require L'Hopital's. So I'm gonna go back and all of this. Yeah, right in front of me. So there are, let me see. There's a lot of different types of indeterminate forms. So here's a not quite comprehensive list. Indeterminate forms. And again, what I want to point out is when I say something is 0, what I mean is it's really small. When I say something is large, what I mean is, or when something is infinity, I mean it's getting very large. So we've already seen 0 over 0 and infinity over infinity. And these are the two where we can just straight up use L'Hopital's rule. But then there's some others. There is infinity minus infinity. There is 0 times infinity. And then there are 3 exponential indeterminate forms. They are, I actually don't remember what they are. Let's see. One sec. They are 0 to the 0. That's definitely indeterminate. It's infinity minus infinity. Yeah. Or plus negative infinity, same thing. It's kind of weird, but yeah, infinity to the 0 is an indeterminate form. And my favorite one, 1 to the infinity. These are all indeterminate. And we'll talk about some of them here. We don't have time to talk about all of them today, but we'll talk about some of them. One that you'll see fairly frequently is 0 times infinity. So either the limit as x goes to 0 from the right, let's say x times the natural log of x. We didn't already do this one, did we? I don't think so. The problem is a lot of these have to look the same after a while. I don't think we did that one. No, we did not. Okay, good. So every time you're dealing with something with L'Hopital's rule or something you think might need L'Hopital's rule, you have to make it look like a fraction. So what I should back up and say is, whenever you see any of these types of indeterminate forms, you're probably going to need to use L'Hopital's rule eventually. This is definitely a 0 times a negative infinity. Right, because as x goes to 0 from the right, natural log goes to negative infinity. So we need to write this as a fraction. Typically, that means taking one of the factors and writing it in the denominator as its reciprocal. So I'm going to rewrite this as, well, I have a choice, and I almost always have a choice. You can either go the limit as x goes to 0 from the right of x divided by the reciprocal of natural log of x, or you could go the limit as x goes to 0 from the right of natural log of x over the reciprocal of x. And there's almost always a better choice. The better choice is usually the one that's going to be less terrible to differentiate whatever's in the bottom. So what's worse to differentiate? 1 over natural log of x or 1 over x? Definitely 1 over natural log of x. That's terrible. You can write that as natural log of x to the -1 and then use the chain rule. But this here, I don't want to deal with that. I'd much rather deal with this, which I can rewrite as the limit as x goes to 0 from the right of the natural log of x over x to the -1st. Both of those things on their own are pretty easy to differentiate. I should back up just a tiny bit. I should point out that when we put this in this fraction like this, the natural log of x is going to negative infinity, and 1 over x is going to positive infinity. So I do indeed have an infinity over infinity form. And that makes sense, excuse me, if you think about it. If you have something that's like 0 times infinity, and you take one of those things and put it in the denominator as its reciprocal, well, it's either going to be infinity divided by 1 over 0. Oh, that's infinity over infinity. or 0 divided by 1 over infinity. Oh, that's 0 over 0. So when you put one of the factors in the denominator as reciprocal, it kind of becomes the other thing. All right, let's finish off this problem. We have the limit as x goes to 0 from the right. The derivative of the natural log of x is 1 over x. The derivative of x to the negative 1 is negative x to the negative second, which I would probably rewrite as the limit as x goes to 0 from the right of 1 over x over negative 1 over x squared. This is a place where you could encounter some danger. You might try using Lobitel's rule again, because if you try plugging in 0 here, you get 1 over 0 on top, which is positive infinity. You get negative 1 over 0 on the bottom, which is negative infinity. You have an infinity over infinity form. Right? This is definitely infinity over negative infinity. Just because you can use a tool doesn't mean you should use a tool. Lobitel's rule is kind of a big tool to use for a limit. People always sometimes there's one people like, it's like trying to kill an ant with a nuclear bomb. People have made that analysis, right? You're using too big a tool. Sometimes it's much easier to do a thing without using the Lobitel's rule atomic bomb equivalent of this is the thing we use, because it's just too powerful. It's unnecessary. Right. Okay, so we can simplify this. That's a 1 over x times a negative x squared over 1. And then we can just cancel an x there and an x there. And say it's the limit as x goes to 0 from the right of negative x. Oh, that's way easier to deal with. That's just going to be 0. All right, so that limit's 0. So this 0 times this infinity, the 0 is I don't know how to say it the right way. The 0 is more powerful than the infinity. The 0 is overpowering how large that is. Because natural log of x doesn't get large very fast. Whereas if you're going to 0, x goes to 0 fairly rapidly. I know that's not super precise, but it's okay. Sure. We'll have to wait to do the exponential forms next time. So we did one of these. Let's do an infinity minus infinity. This can be interesting. Here's a not terrible example. Let's look at the limit as x approaches 1 from the right of 1 over x minus 1 over natural log of x. And I should stress, this is an infinity minus infinity form, right? If x is going to 1 from the right, 1 over 1 minus 1 is 1 over 0, but it's a very small positive number. That's definitely a positive infinity minus, if x is approaching 1 from the right, natural log of 1 is 0, but x is slightly larger than 1. So natural log of x is slightly larger than 0. So this is a 1 over a small positive number, which is still blowing up to positive infinity. This is definitely an infinity minus infinity form. Question? Right, exactly. And then 1 over a small number is a very large number. So fractions always, so I don't have a infinity over 0 over 0. I want to get a fraction. If I have fractions subtracted, the only way to make them one fraction is using a common denominator. So I'm going to write this as the limit as x approaches 1 from the right of natural log of x over natural log of x times x minus 1 minus x minus 1 over x minus 1 times natural log of x. Okay. And I'm going to simplify this a little bit. Right, this is the limit as x approaches 1 from the right. Yeah, I guess I'll just leave the denominator as is. So it's the natural log of x minus x plus 1, x that minus sign distributes, over the natural log of x times x minus 1. And before we get too carried away here, we should make sure, now here's the thing really. As long as you've done the algebra correctly, this infinity minus infinity should turn into a fraction that's either 0 over 0 or infinity over infinity. There's kind of no other choice if all the algebra is done correctly. If you plug in 1 for x, natural log of 1 is 0, x is 1, so 0 minus 1 plus 1, oh yeah, that's 0. And the bottom, if you plug in 1, natural log of 1 is 0, and 1 minus 1 is also 0, so you get 0 on the bottom. So this definitely is a 0 over 0 type. But it's always a good idea to check that you have the right type of thing before you start using Lobitel's rule. So now we're going to use Lobitel's rule, and we're going to get the limit as x goes to 1 from the right. So I'm going to do the derivative of the top, which is 1 over x minus 1. And for the denominator, I have to use the product rule. So the derivative of the natural log of x is 1 over x times x minus 1, plus the natural log of x times the derivative of x minus 1, which is just 1. Before I do anything else, I am going to check and see, can I just plug it in? If I plug in 1, I get 0 on top. That's not necessarily a problem. 0 on top can be fine. If I plug in 1 on the bottom, though, I get 1 times 0, which is 0, plus natural log of 1, which is also 0. So I still get 0 on the bottom. So this is still a 0 over 0 form. So I'm going to use Lobitel's rule again. What I might do first, and I'm curious here what the person would be. Yeah, that's fine. Okay. So I'm going to simplify a tiny bit. Limit as x goes to 1 from the right. I'm going to have 1 over x minus 1 over 1 over x times x is 1. 1 over x times negative 1 is minus 1 over x. Let's use Lobitel's rule one more time. Well, at least, right? Maybe more. I don't know. So I will mention a lot of these examples, you end up taking the derivative of 1 over x a lot. It's good to get very familiar with the fact that the derivative of 1 over x is negative 1 over x squared. We know this. We just usually take a longer route. The derivative of 1 over x is the derivative of x to the negative 1, which is negative x to the negative second, which is negative 1 over x squared. It just feels convenient to write it this way. So I really encourage you to get comfortable with it. Oh yeah, the derivative of 1 over x is just negative 1 over x squared. All right, so then taking the derivative of the top, I'm going to get negative 1 over x squared minus 0. And the bottom, the derivative of 1 is 0. The derivative of negative 1 over x is positive 1 over x squared, right, because the sign changes. And the derivative of the natural log of x is 1 over x. And now if I try plugging in 1, I get a non-indeterminate form. Right? I get something that's a real number. I get negative 1 over 1 over 0 plus 1 plus 1, which is negative 1/2. So here, it sounds weird to say this, but I'm going to say it anyway. Infinity minus infinity was equal to negative 1/2. This infinity was slightly larger than that infinity. How much? By 1/2.